If your stationary altimeter shows you've climbed 100 meters while you slept, the barometric pressure just dropped 12 millibars, and you need to evacuate immediately.
Most hikers rely on probability percentages, but system failure happens at the extremes, not the averages. We need to analyze the rate of change in atmospheric pressure, not just the static reading. A slow decline suggests a passing front. A rapid plunge signals a violent system with high kinetic energy.
Understanding the physics of a pressure drop allows you to anticipate wind velocity before it hits. As pressure falls, the gradient tightens, forcing air to accelerate from high to low pressure zones to restore equilibrium. The steeper the drop, the more violent this equalization process becomes.
Stop looking at relative humidity. It is relative to temperature and useless for gear management. You need the dew point, the absolute temperature at which air becomes saturated. When the ambient temperature drops to within 2 degrees Celsius of the dew point, condensation is thermodynamically inevitable.
This phase change destroys the thermal efficiency of your sleep system. Once down insulation absorbs moisture, its loft collapses, and the trapped air pockets, your primary insulator, vanish. In a single-wall shelter, this physics problem becomes a hypothermia risk. Wind chill is not linear. It follows a convective heat loss curve that accelerates aggressively as wind speed increases. At freezing temperatures, doubling the wind speed doesn't just double the cooling effect. It strips the boundary layer of warm air from your skin exponentially faster. In mountainous terrain, you must account for thermal circulation patterns. During the day, anabatic winds rise up the warmed slopes, but at night, katabatic winds, cold, dense air, drain violently down into the valleys. Setting camp in a depression ensures you are sleeping in a cold air sink. Visual confirmation is your backup to digital data. Stationary, lens-shaped clouds over peaks are lenticulars. They indicate high-velocity laminar flow aloft, meaning severe turbulence is generated on the lee side, capable of shattering tent poles. Conversely, vertical development is the precursor to instability. When you see cumulus clouds transitioning from flat bases to towering heights, the atmosphere is displaying a high lapse rate. The air is rising rapidly, cooling and condensing into a thunderstorm engine. For bikepackers, wind direction changes the physics of load stability. A headwind is an energy problem. A crosswind is a control problem. High-volume seat packs act as sails, creating a yaw moment that can force you into traffic or off a ridgeline. We manage this risk using a binary go-no-go decision matrix. Emotion has no place here. Define your hard limits for wind speed, visibility, and precipitation before you leave the trailhead. If the threshold is breached, the trip is scrubbed, regardless of how much you paid for the flight. The 72-hour framework requires looking at the trend line, not the snapshot. A forecast of rain is useless. Is the system intensifying or dissipating? Are the isobars compressing or spreading out? You are tracking the energy of the system over time.
Finally, calibrate your ABC watch at camp. Since pressure decreases with altitude, if your elevation reading climbs while you are stationary, the ambient pressure is crashing. For every 10 meters of ghost elevation gain, pressure has dropped roughly 1.2 millibars. That is your cue to move.
Forecasts are for planning. Observation is for survival. Stay safe.